There we go. So I'm going to pick up where we left off. The last thing we had was this corollary. Basically, the last thing we kind of did the last time, the corollary is if algebraic field K, then so are alpha, beta, beta, and alpha over beta, if beta is not zero. Okay, so here's kind of the magic of what we did last time. You consider this small tower of fields. Here's the original field K. Alpha is algebraic over K. The extension here must be finite. Right? And beta is algebraic over K. Well, K beta over, so beta is algebraic over K, certainly algebraic over the bigger K alpha, that must be finite as well. So K alpha beta is algebraic over K. So that entire field extension is algebraic over K. Therefore, every element of K alpha beta is algebraic over K. Right? So this includes alpha plus or minus beta, because if alpha and beta are in the field, so is sum or difference, alpha beta and alpha over beta. Beta is not zero. And there you go, right? I mean, it almost feels a little bit like you get something for nothing. This tower gives the extension here is algebraic. So sums, products of these things are algebraic. Let me make an observation to kind of finish this off. If K and F are fields, then so I'm introducing some notation here. K bar sub F, this is the set of everything in F such that alpha is algebraic over K. So what you can do is take this extension here. Now you can jerk out all the elements that are algebraic over K. And this is actually, well, it's a set. It's obviously between F because by definition, and it contains K because notice everything in K is automatically algebraic over itself, right? It's root of the monic polynomial X minus K. And in fact, this set here is actually an intermediate field. This is often called KF is the algebraic closure of the field K in F. Okay. By the way, before I forget, I know some of you might have some questions. And I've got to travel back to Minneapolis today, but I thought after class, if you have time, maybe I could answer some of those questions. If you've got a class after that, just let me know. If you can't stay or whatever you want to, we can work out something for later. So we're going to roll now into the fundamental theorem of Galois theory. In fact, we're going to spend quite a while on Galois theory. The fundamental theorem won't take too terribly long, a few days, and I'll probably get that proved up. But there's a lot of other things that are going on here that I want to impart to you. Galois theory is basically the story of automorphisms. It's a relationship between roots of polynomials and automorphisms of fields, right? It allows you to do things like, in certain cases, count intermediate extensions. Some of the properties they have are reflected in the group of automorphisms of the field. And so this is basically, it underscores an intimate connection between roots of polynomials and automorphisms of the field. Now, I'm going to give you a couple of things to start off, and then I'm going to do an example that I hope we really kind of put a lot of work in getting under the hood on this, because I think the example will sort of, in a concrete way, demonstrate a lot of sort of the major facets of Galois theory. So let's get started here. Let's kind of start with some groundwork. Suppose then if we have we call homomorphism. By the way, as we covered last time in class, fields. But anyway, we call this a K homomorphism. Notice that E and F field extensions of K, so these are both vector spaces over K. So in that sense, this is what I mean by a K module. Let me point out that what this means is that this homomorphism fixes the elements of K. Because notice that if K is in K, then because it's K module homomorphism, you should be able to factor the K out. And of course, sigma 1 is 1 because it's homomorphism. So K module homomorphism means that you're fixing K. Notice that if you have a field homomorphism, then it always has to fix the prime subfield. So if those fields up there are characteristic 0, then it's pretty easy to tell that you have to fix the rational numbers, right? Because 1 has to go to 1, therefore 2 has to go to 2. So now you've fixed all the integers. And once you've fixed all the integers, and note that it's a field homomorphism, then you have to fix all the rational numbers. Is a K automorphism. So sometimes sigma is so an automorphism just means an isomorphism from a field to itself. Okay. Let me also point this out. Hey, automorphisms of F. That is the automorphisms, the automorphisms of F to itself, the fixed K, is called the Galois group of F over K. So the Galois group of F over K. And let me give you some notations that you might see. Galois group of F over K. This is synonymous with the automorphism group of F over K. Sometimes people are really lazy and write GF. Do that sometimes. Let me point out that the set of automorphisms form a group under function composition, right? If you have then you can compose these to have another automorphism, because the composition of two functions that are both one-to-one and onto is one-to-one and onto. Composition of homomorphisms is a homomorphism. And of course, it's a group because of the fact these are automorphisms, they all have inverses. And of course, you know, you've always got at least the identity homomorphism as well. Right. Any questions so far? Okay, let me start off with an example, and then I'll build up to a bigger one. You'll see some seeds of almost high school stuff that comes out of this. CV is square-free integer, and what this means is the only square in D, square, I mean square in the integers, is so -1 is a square-free integer, so is 6. But -4 and 12 are not square-free integers because with the examples I gave, they're both divisible by the square of 4. By the way, anybody want to take a guess as to at this point, now that I've got the example started up with Q inside Q radical D, why do we care that D is square free? Anybody want to venture a guess? Well, I'll put this extension here to be honest. So let me kind of scribble it over here. If we had something like Q inside Q square root of 4, well, what's the smallest field containing Q in the square root of 4? Well, it's just Q, because that's just 2. And I want this to be something non-trivial. And of course, even if you had something like this, because this is just 2 times radical 3, right? So this is just a technicality here. Anybody want to guess the Galois group? What are the automorphisms of Q radical D that fix Q? Anybody want to guess how big the Galois group is, what the structure is? Anything like that?
Is it something like C2 or something like that?
You're exactly right. It's Z2. Let me tell you what the automorphisms are. This is so. Let me give you the spoiler here. There are exactly 2 automorphisms here. One of them is the identity. So that would be one more. Here's the non-trivial one. Sigma. And here, A and B are rational numbers, right? A general element of Q radical D. Maybe I should write this. This is the set of elements A plus B radical D, where A and B are rational. Anybody want to guess what the automorphism does to this?
A minus B square root of D?
That's right. This is just like the old high school thing where, you know, your teacher may have said, oh, look, rationalize this denominator or something like this. What your teacher was really doing was asking you to multiply something by its conjugate, so to speak, right? Notice it's easy to check, and I'll leave that as an exercise, that this is actually an automorphism. The hardest part is showing that it works multiplicatively. Additively is easy. Showing that alpha beta is sigma alpha, sigma beta. It's not hard, but it's a little bit tedious because you've got to multiply these things out, but it's not a big deal. This is actually an automorphism. Once you know that it's a homomorphism, it's clearly onto, right? Because if you want to get to A plus B radical D, start with A minus B radical D. And it's 1-to-1 to get that automatically because these are both fields, right? You don't even have to verify that. And has to be 1-to-1. Now, this came up maybe in high school when you did things like, you know, tried to rationalize 1 over 1 plus radical 2 or something like that. You multiply by its conjugate. This also comes up if you were to solve this. I'm embarrassed to do this in a class that begins with an 8, so keep it quiet, but I'm going to do it anyway. Here's the quadratic formula. A squared minus 4b over 2. Notice that you have two roots here, plus or minus what's under the radical. This is very familiar. This is not a coincidence, right? That the way this automorphism works is if this were an element of the field, right? If that thing under here was a, say, square root of D, the automorphism would take one root to the other root, right? This is not a coincidence. And let me, and in fact, these are the only automorphisms. I'm going to give you a result that'll help us see this in a minute. These are the only automorphisms. And notice what happens here. Of course, you've got a group with only two elements in it, so it's probably not surprising here that this has to be Z2 structure. You have two automorphisms here. You have the identity automorphism, which we noted earlier. You have the sigma. And what happens when you compose sigma with itself? The identity. Because what happens when you conjugate something and conjugate it back? Everybody okay with that? Let me make a very important observation. We have done this implicitly in the previous stuff when we talked earlier about fields, but let me point this out a little bit. Okay. Actually, and let's let f of x suppose f is a field containing field extension. It contains A and it contains all the roots of this polynomial. Now, such a field exists, and we're going to be more specific about this later. But let me kind of give you a feel for why there is a field that contains roots of this. Take your polynomial. Right? Now look at the field. We'll call this field E1. Notice that E1, you've seen this before in class, is a field AX mod. Now E1 contains a root path. Now, in E1, X has a root. So it factors. It has that root in there, and then it has a G of X. The roots, it might be a product. But what you can do is you now take this G of X and by looking at just take the irreducible factor. G prime of X is an irreducible factor of A. Now you've got sort of the second root of X, and you just you can always do this. Suppose you have a field, and you have an extension field of in a polynomial that's irreducible. Suppose you have an extension field that contains K and all the roots, And of course, if you're in characteristic 2 and your base field is K, you know there is such a field from experience as well, because you can just pick the complex numbers. But let me point out that suppose you have an element of the Galois group of F over K. So this is an automorphism of F that fixes K. Then sigma must K any root of F of X to another root of F of X. This is an incredibly important observation. Anything in the Galois group, you have an irreducible polynomial over K, anything in the Galois group takes a root of F of X to some other root. And let me show you why that's true. Suppose that this is the irreducible polynomial that we talked about. Let alpha be a root of F of X in F. Alpha is some root of that. So this means that A0 plus A1 alpha plus A2 alpha squared plus AN alpha n is 0, right? Because that's what it needs to be a root. Now, apply your favorite element of the Galois group. Apply your favorite element, sigma of the Galois group, to both sides of this equation. And of course, the left-hand side is 0. And when you apply sigma to this big chunk here, remember, sigma 0, A1 alpha, A2 alpha squared, sigma AN alpha n. Sigma is an element Galois group of F over K. And each of those subscripted A's are in K. So it's sigma alpha, finally AN, and this is sigma alpha to the n. Here liberally using homomorphism. You see, F. So, an important observation, because so any sigma in Galois group of F over K induces a permutation of the roots of F of X, where F of X is again irreducible over K. Questions on that? This is a very important observation here, that automorphisms take roots to roots. Okay. Okay. So I'm going to do this big example here that I promised. And I want you all to try to help me figure. Here's what I'm going to do. My seeds are this. You're going to start with Q. So one root of this polynomial, I think very obviously, is the cube root of 2. I am also going to conjugate roots to this that correspond to the following. So roots are alpha, alpha omega, and alpha omega squared, which is saying are square. Third root unity. When you have 5, if you haven't seen it before, where this comes from, if I have a polynomial, omega is root of x cubed minus 1. Notice that x cubed minus 1, x squared is 1. Now, of course, one root of this polynomial is 1. Right? Two roots of 1. Therefore, 1 plus that's where notice one root is this, and I'll assign it there. And omega squared is minus 1 root minus 3 far. Notice that we have that omega cubed 1. That we have omega squared plus omega plus 1 is equal to 0. Because both of these omegas actually are. Okay with that? These three roots of this. You cube this, you get omega cubed. And when you cube this, you get alpha cubed times omega to the 6, which is I am going to, so Galois group, Wells field that contains all the roots. Well, to get all the roots of these polynomials, I got to get one of the roots, so I'm going to stick on the cube root of 2. Notice, cube root of 2 does not get all the roots of the polynomial here. Not real, right? And if I stick on just cube root of 2, it's going to be a real extension. So I'm also going to throw in omega. This is actually a smallest field that has all three. But notice now I've got alpha omega, and alpha omega squared. Notice if I have all these three roots in the first place, and it's a field, then I have to have this divided by this, which is omega. So it's necessary that I have omega in there. How big is this big? We've already remarked that it's a group, right? How big can it be? And basically, I've built this extension just by sticking on roots of this crazy polynomial. Can anybody give me an upper bound for how big that can be?
6.
6. That is correct. Where'd you get that?
Because you just said before that it induces a permutation of the roots. So we have 3 roots. So there are 6 different permutations
That is
of
correct.
2 elements.
Very, very nice. Very nice. So we've got 3 roots, right? And as you pointed out, we just said that any automorphism induces a permutation. Well, the number of permutations on 3 elements is 6 of them. So it looks like that's as big as I can do, right? And in fact, it turns out in this particular example that I get them all. And it turns out, we'll go through this, a basis for this is actually an algebraic extension, and we're going to be more precise about this, but basically you have to jump degree 3 root of that cubic polynomial. Complex, you have to jump to root 2. It's actually degree 6, and you can verify this directly by showing that a basis for this consists of 1 alpha squared, omega alpha, and omega alpha squared. You can actually show that this is a linearly independent set and forms a basis. Now, what I want to do is I want to figure out my entire list of automorphisms. And these automorphisms, basically, all I really need to do is know what they do to alpha and omega, but I'm going to figure out what it does to the entire basis, because I think that might be more illustrative here. So here's the basis: 1 alpha squared, omega alpha squared. And what I'm going to do is I am going to number the roots. So I'm going to introduce kind of a notation here. I am going to number the roots this way. Let me go back to the previous board here. One, 2, 3. We'll be working sort of. First thing I'm going to do is easy. The first thing I'm going to do is I'm going to define identity. Okay, certainly I've got the identity automorphism. What does the identity do to each of these? Oh, that's easy peasy. Actually, maybe I should. So there we go. That was easy. Now I want to look at phi 1, 2. Okay, let me tell you what I mean by this notation. I want the automorphism induced by trying to flip out these 2 roots. I want to take alpha to alpha omega, alpha omega to alpha, and I want to leave this 3rd root alone. Okay. Well, 1 better go to 1. That's always going to be the case. And I want alpha to go to alpha omega, so here we go. Now, really to finish this off, I really need to know where omega goes. Can anybody tell me if I flip out, if I swap alpha and alpha omega, take alpha to alpha omega and alpha omega to alpha, where does omega have to go? Let me do a little computation here. It goes to alpha omega. alpha omega goes to alpha. So what happens to omega? Right now? Well, think of it this way. Alpha goes to alpha omega. Alpha omega goes here. What if I divide this by this? Alpha omega over alpha is omega. This quotient here, which is omega inverse. But I don't have omega. What is omega inverse here?
Omega square.
It is omega squared. And the reason it is because look back at this. Omega cubed squared is omega inverse. Omega always has to go to either omega or omega squared because omega is the root of this. And there are two roots, omega and omega squared. Any automorphism has two swap roots. So across this line here, omega is always going to either omega or omega squared. Once I've got this, I've totally got this licked because this now alpha squared now goes to the square of this, which is alpha squared omega squared. And omega alpha should go to, just find out where alpha goes and omega goes and multiply. This should go to alpha. And omega alpha squared should go to alpha omega to the fourth, which is alpha squared. Make sure I agree with what I did. Okay, any questions on that? Okay, how about this one? P of 1, 3. Well, what this one does is this one is attempting, let's see, 1, 3. This attempts to take alpha squared and alpha omega squared alpha. And it should leave alpha omega alone. Let's see what happens. Alpha goes to alpha omega squared. Alpha squared should go to the square of that, so that should be alpha squared omega to the fourth, which is omega. Now, again, I can ask myself, where does omega go? Anybody? Can have y'all figured out where omega goes? What do you think? Well, I can do this kind of thing trick again. Let's divide. Omega squared goes to this over this, goes to this divided by this, omega minus 2, which is omega. So omega squared goes to omega. So in other words, omega squared goes to omega, which means that omega has to go to omega squared. Just square this. If you square this, you get omega, square this, omega squared. So this goes to omega squared. Now, here's kind of a big test because in this one, alpha omega had to be left alone. Let's see what happens. Where does alpha omega go? It should go to the product of this and this. This is alpha omega fourth, which is alpha omega. So big smile, it works. That one alone. And the last one should go, let's see, omega alpha squared, this product here, this should go just to alpha squared. Okay, so far? Here's the next one, by the way. This one's a fun one. If you pay attention, this one's a familiar automorphism. So this one, what we're trying to do is we're trying to flip out 2 and 3 roots. So we want alpha omega go to alpha omega squared. We want alpha omega squared go to alpha omega. And I want alpha itself to be left alone. Anybody know this is a familiar automorphism? Anybody know what this one is? It has a kind of complex name, but it's really, well, let's see. Let's actually get some of those filled in and see if you recognize it. This goes to 1, and alpha should go to itself, but you know what? I'm gonna let's kind of test that out. We'll see. What do I get from this? If I take this and divide by this, I get omega. That should be this divided by this, omega inverse, which is squared. So this goes to omega squared, right? If I square this one, alpha squared omega squared goes to alpha squared omega. So now I can take this and divide by this and get alpha. This divided by this gives me alpha, and this divided by this gives me alpha is fixed, which is good. That's what we want. That means that alpha squared goes to alpha squared. And now I can just take the rest of this off. Alpha omega goes to alpha omega squared. And alpha squared omega goes to alpha squared. Does anybody recognize this one? Do I recognize this automorphism? Alpha and alpha squared are real. They were all left alone. But notice all these things here that were complex or not real got conjugated. It's complex. And are doing our business roots.
Prof, can you please write a little bit bigger because we have problems in the top of the board?
Problem seeing this.
Yeah, those 2 lines, we cannot see them correctly.
Okay. So let me, okay. Yeah, I'll write this a little bit. Can everybody see the table? Were you able to see it when you looked like on the replay of the video? Okay. I'll make this last one really kind of gargantuan. Okay, what about this one right here? Uh-oh. Did I really just kill that? Well, I'll just do this. Okay, so what am I doing with this one? This last one, I want to take alpha to alpha. Let's take alpha to alpha omega to alpha omega squared, alpha omega squared to alpha. So I've got to do that little free dance. See how that works. Well, alpha goes to alpha omega. And really all I need to know now is where omega goes. I guess I can get that this way. This divided by this. Alpha omega over alpha is omega. And this divided by this is omega. Omega. Yeah. And so, all right, that goes to omega. So my alpha squared goes to alpha squared omega squared. And let's see, omega alpha So where does omega alpha go? It should go to the product of this and this, which is alpha omega squared. And how about omega alpha squared? It should go to the product of this and this, which is alpha squared. Okay, any questions on that? Okay, see if you can get the last column. There's a couple of ways you can do it. You can do it the way that I did it, or actually, the square of this should be the permutation for the last column. You should check that. See if you can work your way through that. And I'm going to reproduce this table next time. I'll be back on Friday, good Lord willing. And I'm going to use this table to kind of look at what's going on between this big field here, Q alpha, omega, and Q. Okay, any questions on that before we break for the day?
I have a question. So are we not required to send the basis elements to other basis elements because we're getting like
No, absolutely not. Because it could be like a change of basis, right? So when you did in linear algebra, like linear transformations, you can send the standard basis E1, E2 to some other linearly independent set if you like.
Oh, okay, that makes sense.
Okay, other questions? Okay, I'm going to stop the recording and see if